Let us see protection and deprotection of alcohol. The best example, the bud of lotus, in which colored petals get protected by the green sepals. It is protection of flower. But early in the morning, these flowers opens exposed to the environment, means it gets deprotected. Chemicals are also the part of nature. These chemicals undergoes protection and deprotection, and we are using this phenomenon in our synthesis. Now let us move towards protection and deprotection of alcohol. In some organic compound, it contains more than one functional group. Now see in this example, 3-hydroxypropanaldehyde. There are two functional groups, hydroxy as well as the aldehyde. If we treat this compound with a strong oxidizing agent, chromium trioxide, both the functional group undergoes oxidation to form the malonic acid. Means here we loses, this reaction loses this selectivity. But see here, if we want to oxidize only this aldehyde group and want to intact this hydroxy group as it is, here we have to block this hydroxy group, and for blocking or for deactivating this hydroxy group we are using some reagent. That reagents are called as the protecting reagent, and the group is called as protecting group. Here dihydropyrin is used as a protecting reagent for the protection of this hydroxy group, which blocks this hydroxy or the alcohol group, and on oxidation only aldehyde group get oxidized into the acid, so we get 3-hydroxypropionic acid. This is the example of protection and deprotection of hydroxy group. Now see protecting groups. Protecting group is a molecular framework that is introduced on the specific functional group. See here, dihydropyrin, this protecting group is introduced to the hydroxy group. This is the specific functional group in a polyfunctional molecule to block its reactivity under reaction conditions, to make modification elsewhere in the molecule. Here we are modifying this aldehyde group into the carboxylic group. This is called as the protecting group. In this reaction, dihydropyrin is used as a protecting group for alcohol to block the activity of alcohol and oxidizes aldehyde to the acid. Here BF3 and H positive. This reagent is used for the deprotection of alcohol. Now, the qualities of good protecting group in organic synthesis. The first quality, it should be simple to put on the reactive part. It's that reagent should be stable in subsequent reaction steps in which the group being protected is desired to remain deactivated. Means in the reaction, in the completion of reaction, it should be deactivated, and that protecting group should be easy to remove after completion of reaction. And the last point, it should favor a high yield of reaction. These are all the qualities of good protecting group. Now we are moving towards the protection of alcohol. Why it's necessary to protect the alcohol group? The lone pair present on the oxygen atom of alcohol gives nucleophilicity to a hydroxy compound. Alcohol reacts with oxidizing agents and get converted into the carbonyl compound, while it also reacts with alkyl halide and acyl halides to give ether and esters. If the reaction at selected hydroxy sites are to be avoided, if we want to block this hydroxy group, its nucleophilic behavior must be avoided or deactivated by using various protecting groups. Now see, These are the some important protecting group. First, acetal or ketals as a protecting group. Second, common silicon based protecting groups for alcohol. Ether as a protecting groups for alcohol. And last, here we are discussing ester as a protecting group for alcohol. Now we are discussing these four protecting group here. First example, acetals or ketals as a protecting group for alcohol. Here, tetrahydropyrenyl derivative. This tetrahydropyrenyl derivative, see here in this reaction, it is the protecting group for the hydroxyl group. In this example, propane 1,3-diol. If we want to oxidize this propane 1,3-diol into the 3-hydroxypropionic acid, means we want here selective oxidation, only oxidation of this first hydroxy group, and we want this third hydroxy group or second hydroxy group attached to the third carbon atom as it is. So we want to protect this hydroxy group. Here, while protecting the step first, see here, in dihydropyrene, H positive adds on this third carbon atom, lone pair shift here, and double bond formation, forming positive charge on the oxygen atom. This oxygen becomes electron deficient. The lone pair of the oxygen atom attack on this carbon atom, shifting lone pair on the oxygen. Now this oxygen atom becomes electron deficient. So on loss of H positive ion, we get this stable compound. Now this compound, or we call it as the tetrahydropyrenyl derivative. Now this tetrahydropyrenyl derivative is subjected to the oxidizing agent chromium trioxide, which is a strong oxidizing agent. It oxidizes only this first hydroxy group into the carboxylic group, COOH. Now here our reaction target is complete. So now we want to remove this hydroxy, we want to deprotect this hydroxy group. For the deprotection of hydroxy group, in first acidic condition, in presence of boron trifluoride, H positive adds on the oxygen atom, lone pair of the oxygen atom. This oxygen become electron deficient, and the boron trifluoride, fluoride ion plays a role. The bond between oxygen and this ring, the lone pair shift on the oxygen atom. Here we get our desired target molecule. This is the example of protection and deprotection of alcohol. Second example, see in this starting molecule, here we are going to introduce COOH group attached to the sp hybridized carbon atom. Here this hydrogen atom as well as hydroxy group both are reactive to the Grignard reagent. So here it's necessary, if you want to introduce this COOH group to this carbon atom, OH group should be blocked. So the first step, protection of this hydroxy group with the dihydropyrene to form tetrahydropyrenyl derivative. Then subject this compound to the methyl magnesium bromide in presence of ether. Now methyl magnesium bromide react only to this proton, CH3 negative abstract this H positive, and MgBr forms complex with this compound. Now this complex, again this nucleophilic carbon atom attack on the carbonyl carbon atom of carbon dioxide. This lone pair shift on the oxygen atoms. See these arrows, shifting of lone pair on this carbonyl carbon atom, and pi bond opens on this oxygen atom, formation of O negative here. MgBr again forms second complex with this O negative of carbon dioxide. Now it's time to break this complex on hydrolysis, H positive and OH negative goes to the react with the MgPr to form COOH group. Here our reaction target complete. Now we want to remove this ring. We want to deactivate this hydroxy group on reaction with H positive and boron trifluoride. This hydroxy group get again deprotected to form our final compound. Here hydroxy group remain as it is by blocking it and deprotecting it. Now this is the third example in which propane 1,3-diol. Here we want to introduce this C6H5 phenyl ring to this first carbon atom. So obviously second hydroxy group should be blocked. Reactivity of this second hydroxy group blocked means protect. We have to protect this hydroxy group. See here in the first step with dihydropyrin ring, here we have protected this hydroxy group to form the tetrahydropyranyl derivative. Then on oxidation with this pyridinium chlorochromate, this is a mild oxidizing agent. It oxidizes this hydroxy group into the aldehyde group. Now this tetrahydropyranyl derivative on reaction with phenyl magnesium bromide in presence of ether, this phenyl ring attack on this carbonyl carbon atom, opening of pi bond on the oxygen, then formation of MgBr complex which on hydrolysis break to give this product in which phenyl ring introduced on this carbon atom. Now to get desired product, here necessity to deprotect this tetrahydropyranyl derivative in presence of BF3H positive. Here we are deprotecting this group to get our final compound, to get our desired compound. This is the application of protection and deprotection of hydroxy group in presence of dihydropyrin. Now the second type of protecting group for the hydroxy group, it is common silicon based protecting groups. Now these are the three examples of the silicon based protecting group. First, trimethylsilyl ether. Second, tertiary butyl dimethylsilyl ether. And third, triethylsilyl ether. Here how these silicon based protecting group form. See the protection. Alcohol reacts with triethylsilyl chloride, HCl removed, and this triethylsilyl ether forms. Now this hydroxy group get protected by forming a bond with the silicon. This triethylsilyl ether on reaction with fluoride ion, fluoride attack on the silyl, then negative charge formation on this silane atom. So this the bond of electron pair oxygen and silicon atom opens on this hydroxy group or the oxygen atom to form this alkoxy ion, and finally H positive adds to form the alcohol. Here we deprotected alcohol, recovered our alcohol by using this fluoride HF. Now see the synthetic application of silyl protecting groups. In this compound, if this compound directly reacted with metachloropurbenzoic acid, it gives epoxide cis to the hydroxyl group. But if we want a selective epoxidation of this compound, then here we have to protect this hydroxy group with tertiary butyl dimethylsilyl chloride. This is the short form of tertiary butyl dimethylsilyl chloride. HCl removed and there is a formation of tertiary butyl dimethylsilyl ether. This is the protecting group. Now this trimethylsilyl tertiary butyl dimethylsilyl ether on reaction with metachloroperbenzoic acid, this derivative on reaction gives epoxidation. Now see here, the bulkiness of tertiary butyl dimethylsilyl group, ether protecting groups, can be used to approach this incoming reagent from the less hinder side, because due to its bulkiness, this incoming reagent enters from the less hinder side. So we get here epoxide trans to this bulky group. Now finally deprotect this hydroxy group by using tertiary N tetra N butyl ammonium fluoride. Now see here, fluoride goes here, and on addition of H positive, we recover this hydroxy group to get our desired product. In this way, this is the one of the application of silyl protecting group. Second, the bulkiness of tertiary butyl dimethylsilyl ether protecting group can also exploited in incorporating the protecting group on less sterically encumbered primary hydroxyl group selectively using silyl chloride. See here, this is primary hydroxy group. Here, this bulky group, we are applying this bulky silyl chloride group. This tertiary butyl dimethylsilyl chloride adds on this primary hydroxy group. So this hydroxy group gets blocked. Now subject or treat this compound with this mild oxidizing agent pyridinium chlorochromate. It oxidizes the secondary hydroxy group into the ketonic group. Now tertiary butyl tetra-tertiary butyl ammonium fluoride. This reagent used for the deprotection of this hydroxy group, and this hydroxy group get deprotected to form our compound. The next example, ether. This is the third protecting group we are discussing now. Ether as a protecting group for alcohol. Alcohols can be easily converted into ether in basic medium. See here, this is primary hydroxy group and this one is the secondary hydroxy group. When this compound is treated with the methyl chloride or methyl alcohol in presence of base, HCl removed and formation of methoxy group. In this way we have protected here hydroxy group, converted this hydroxy group into the methoxy group. Now on reaction with Collins reagent chromium trioxide in presence of pyridine and dichloromethane, this hydroxy group gets oxidizes into the ketonic group. Here we selectively oxidize this hydroxy group by protecting or by deactivating this hydroxy group. Now it's time to deprotect this hydroxy group because our reaction is complete here. By using boron tribromide in presence of aqueous condition, we deprotect this methoxy group into the hydroxy group. In this way, we selectively oxidize this secondary hydroxy group into the ketonic group, and this primary hydroxy group remain as it is. This is the best example of selective oxidation using ether as a protecting group for the alcohol. The second example, Grignard reagent, here we are using Grignard reagent. See, we are introducing this phenyl ring to this carbonyl carbon atom. But Grignard reagent is reactive to both hydroxyl as well as the ketonic group. So here there is necessity to block this hydroxy group in presence of methyl iodide. The reactivity of hydroxy group gets blocked to form methoxy group. Here we protected hydroxy group. This is the first step, protection of hydroxy group in presence of base. Now the compound, this ether derivative of hydroxy group, when treated with phenyl magnesium bromide Grignard reagent in presence of ether, this phenyl ring acts on this carbonyl carbon atom, formation of this MgBr complex, which is treated on, or which on hydrolysis gives hydroxy group. See here, the reaction, our desired reaction complete here. Now it's time to deprotect hydroxy group to achieve the final compound. On reaction with boron tribromide in aqueous condition, hydroxy group gets deprotected. So here we achieve the final desired compound. And the last protecting group is ester as a protecting group for the alcohol. The first example is the formate ester. Formation of formate ester. When hydroxy group, in the protection of hydroxy group, when hydroxy group treated with the formic acid, see, the lone pair of hydroxy group attack on the carbonyl carbon atom, pi bonds open on the oxygen atom, formation of O negative. So OH group removed here, and the bond formed between this oxygen and the carbon atom, H positive on the loss of this H positive ion. See, with the help of this arrow we can explain the mechanism. So formation of this formate ester, this is the protected form of hydroxy group. Now we can deprotect this formate ester by reacting it with the dilute ammonia, or by reacting it with the ammonia solution. This lone pair of nitrogen atom attack on the carbonyl carbon atom, pi bond opens on the oxygen, and this OR negative group open, removed to form the ROH, our hydroxy group recovered in the last step. This is the deprotection of hydroxy group. Second example is the benzoate ester. In the benzoate ester formation, hydroxy group treated with the benzoyl chloride to form the benzoate ester. See here again, lone pair attack on the carbonyl carbon of benzoyl chloride, pi bond opens on the oxygen atom, and the chloride ion removes here. The bond formed between this carbon atom and the oxygen atom on removal of H positive ion, it forms benzoate ester. Now this is the protection of alcohol hydroxy compound with benzoyl chloride to form the benzoate ester. The second step, deprotection, in presence of strong base sodium hydroxide and methyl alcohol, the hydroxy ion attack on the carbonyl carbon atom, lone pair opens, formation of O negative here, OR negative, this leaving group removes to restore double bond, and on reaction with H positive it forms our hydroxy group get recovered or deprotected. This is the reaction of benzoate ester, protection as a of hydroxy group. Third example is the acetate ester as a protecting group. See here, we can protect hydroxy group to form acetate ester by using these three reagents. First acetic acid, then second acetyl chloride, and the third acetic anhydride. Now see the mechanism. The lone pair of hydroxy group shifts toward the carbonyl carbon atom, pi bond opens on the oxygen atom, and hydroxide ion removes to restore the double bond, and hence there is a formation of this acetate ester. When we use acetyl chloride, again similar pattern, similar mechanism. The lone pair shifts on the carbonyl carbon of acetyl chloride, pi bond opens on the oxygen atom, and again chloride ion removes here to restore double bond. On loss of H positive ion, we get here acetate ester. And the third example, in case of acetic anhydride, again the lone pair of oxygen atom shifts toward the carbonyl carbon atom, pi bond opens on the oxygen. Now here this is the removing group, acetate group, to form the acetic acid CH3COOH to restore the double bond on loss of H positive ion to form the acetate ester. In this way, formation of acetate ester from this acetic acid, acetyl chloride, and the acetic anhydride. This is the protection of hydroxyl group. Now we want to deprotect this acetate ester. Here we are using potassium cyanide in presence of ethyl alcohol. The lone pair of cyanide, see here the mechanism. Cn negative shifts towards the carbonyl carbon of this acetate ester, pi bond opens, and this OR negative removes as a leaving group, which on reaction with H positive recovered our hydroxy group. This is the deprotection step of acetate ester. Next ether protecting group is the alkyl methyl carbonate ester. Here hydroxy group on reaction with this reagent, lone pair shift on this carbonyl carbon, pi bond opens, and chloride ion, on removal of chloride ion, here there is a formation of alkyl methyl carbonate ester. This alkyl methyl carbonate ester, it is the protection of hydroxy group. This alkyl methyl carbonate ester on decarboxylation gives recovered hydroxyl group. Here we recovered or deprotected this hydroxy group. These are all about the protection and deprotection of hydroxy group. Friends, here we discuss the 4 important protecting groups of hydroxyl group. Those are acetal or ketals, in which we discuss the tetrahydropyrenyl derivative as a protecting group. Then common silicon based protecting groups. Then third one is the ether as a protecting group, and fourth one ester as a protecting group. These are all about the protection of hydroxy group.